NASA tells us today it's found a new planet, and it is a lot like the Earth.
NASA just announced the discovery of other stars, not our sun, but one of them shares some similarities with Earth.
Imagine a world much like our own, but just a bit larger. What kind of life would it host? Would there be intelligent species much like us down there? Well, we may be able to find out soon because we just spotted a planet like this, lurking only 137 light-years away. This may sound like a lot, but it's only a stone's throw in cosmic terms. This is TOI 715b, a recently discovered super-Earth that's stirring excitement across the scientific community. While exoplanets like this are often found hundreds, even thousands of light-years away, TOI 715b is a close neighbor. So, what can we expect now that NASA has found a super-Earth planet just around the corner? Let's dive straight in. A habitable planet not so far away. TOI 715b is a fascinating new addition to the family of exoplanets and an exceptional example of a super-Earth located within the habitable zone of its host star, TOI 715. Discovered in 2023 by NASA's Transiting Exoplanet Survey Satellite, or TESS, TOI 715b is noteworthy for its proximity to our world, being a mere 137 light-years away, which offers a rare opportunity for in-depth study with relatively accessible observational technology. This planet has sparked substantial interest in the scientific community due to its size, its location within the so-called conservative habitable zone, and the potential it holds for further examination by advanced telescopes such as the James Webb Space Telescope. Could this super-Earth be housing intelligent life like ours? If so, then are we on the verge of establishing first contact with extraterrestrials? Well, there's a lot to unpack, so let's get started. TOI 715b is called super-Earth simply because it is slightly larger than Earth, but smaller than the ice giants in our solar system, such as Uranus and Neptune. Measuring about 1.55 times the size of Earth, TOI 715b is massive enough to retain a thick atmosphere and, as a result, maintain liquid water, which is a key ingredient for life as we know it. This size also suggests that it has a higher gravitational pull than Earth, which could impact atmospheric retention and surface conditions, but it remains within a range that allows for a rocky, Earth-like composition rather than a gas-dominated one. So, essentially, we're looking at a second Earth, only slightly bigger, and not all too far away either. Much like our Earth, the TOI 715b is located within the habitable zone, or the Goldilocks zone, of its host star, TOI 715, an M-type, or red dwarf star. Red dwarfs are smaller and cooler than stars like our Sun, and their habitable zones are correspondingly closer to the star. In the case of TOI 715b, the planet orbits at just 12.4 million kilometers from its star, significantly closer than Earth's distance from the Sun, which is 150 million kilometers. This close orbit, however, doesn't expose the planet to intense heat, as red dwarf stars emit lower energy levels than larger stars. Instead, the equilibrium temperature of TOI 715b, which is the average temperature that the planet would naturally reach due to the heat it receives from its star, assuming it has no atmosphere to retain or distribute heat, is estimated at around minus 39 degrees Celsius. This temperature is cold by Earth standards, much lower than the freezing point of water, but it doesn't entirely exclude the possibility of liquid water. This is because, if TOI 715b has an atmosphere, it could potentially trap some of the star's heat, warming the planet beyond this baseline temperature. This warming effect could occur if TOI 715b's atmosphere contains gases like carbon dioxide or methane, which are known to trap heat efficiently. This process, known as the greenhouse effect, is how Earth retains heat, keeping our planet warm enough to support life. With an atmosphere that includes greenhouse gases, TOI 715b's surface could be warmer, potentially reaching temperatures where liquid water could exist. The discovery of TOI 715b is groundbreaking for NASA's Transiting Exoplanet Survey Satellite, or TESS, as it marks the first time that this survey satellite has detected a planet within the conservative habitable zone. Now, what does that mean? Let's find out. The conservative habitable zone. The conservative habitable zone is the area around a star where a planet could have the right conditions for liquid water. The idea is that if a planet is in this region, it might not be too hot or too cold, kind of like the story of Goldilocks and the Three Bears. It could be just right for life. In 2014, scientists led by Ravi Kopparapu worked on defining this zone with very specific numbers to make sure we're looking at planets with the best chance of having liquid water. For Earth, we get a certain amount of energy, or sunlight, from our sun. This energy is called insolation. Planets in a star's conservative habitable zone receive sunlight that's between 42% and 84% of the energy Earth gets from the sun. That means the planet wouldn't be too hot, like Mercury or Venus, which are closer to the sun, and it wouldn't be too cold like the outer planets. Now, TOI 715b receives about 67% of the sunlight that Earth gets from our sun. Scientists write this as 0.67 times Earth's insolation. For comparison, if Earth's energy from the sun is like a whole pie, TOI 715b gets a little more than 2/3 of that pie. This amount of sunlight is within the safe, conservative habitable zone, so the planet's temperature could be suitable for water to stay liquid rather than evaporating or freezing. There's a little bit of uncertainty here, because the sunlight TOI 715b receives could be as low as 47% or as high as 82% of Earth's, depending on small changes in its orbit or star's brightness. Either extreme is still within the conservative habitable limit. This is a key reason scientists think this planet could be similar to Earth in terms of its environment, especially when you consider that it's only about 50% larger than Earth. With this balance of sunlight, TOI 715b has a real chance of being warm enough for liquid water to exist on its surface if other conditions, like an atmosphere, are also right. Finding a planet like TOI 715b within this habitable zone is a huge deal, and there is good reason to want to study it further. The next steps, like using the James Webb Space Telescope, might reveal even more about its surface and atmosphere, helping us understand if TOI 715b could support life. If we find that TOI 715b has an atmosphere with water vapor or other signs of life, it would be one of the most Earth-like planets discovered so far, and a huge milestone in the search for extraterrestrial life. Before diving any deeper into the planet's features, let's take a look at its surroundings. The red dwarf star, host to TOI 715b. TOI 715 is a fascinating red dwarf star situated around 140 light-years away from Earth in the constellation Volans, located near the southern celestial pole. While it may be relatively close in cosmic terms, it's far too faint to be seen with the naked eye or even with a small telescope. But this star has now gained interest for hosting at least one confirmed exoplanet in its habitable zone, TOI 715b, a super-Earth. TOI 715 belongs to the most common category of stars in the universe. Red dwarfs are smaller, cooler, and far less luminous than stars like our Sun, meaning they don't shine brightly enough to be visible without advanced telescopes. Specifically, TOI 715 has only about 24% of the Sun's radius and 23% of its mass. Its surface temperature is around 2,802 degrees Celsius, which is much cooler than the Sun's surface temperature of about 5,499 degrees Celsius. This cooler temperature gives red dwarfs their characteristic dim red appearance and makes them burn fuel at a much slower rate than hotter, larger stars. This slow burn means red dwarfs like TOI 715 have impressively long lifespans, often trillions of years, far longer than our Sun's estimated lifespan of about 10 billion years. TOI 715 is not only cooler, but also older than our Sun, with an estimated age of around 6.6 billion years, which could vary by as much as 2 to 3 billion years on either side. This greater age implies that TOI 715 has a lower level of magnetic activity compared to younger stars, which often exhibit more solar flares and magnetic storms. Since increased magnetic activity can produce harmful radiation, and TOI 715 does not exhibit this kind of agitation, its planets, like TOI 715b, are less exposed to intense stellar flares that could strip atmospheres and make conditions harsh for life. Another interesting detail about TOI 715 is its metallicity, which refers to the abundance of elements heavier than hydrogen and helium within the star. TOI 715 has about 23% more of these elements compared to our Sun. In astronomy, a higher metallicity is significant because it often correlates with a star's potential to host rocky planets. Metals like iron, carbon, and oxygen contribute to the formation of terrestrial planets, so TOI 715's slightly higher metallicity may have helped in forming rocky exoplanets like TOI 715b. The presence of TOI 715b in TOI 715's habitable zone, combined with the star's characteristics, makes it a particularly compelling system for astronomers. Additionally, because TOI 715 will burn steadily for billions of years more, it will give any planets orbiting it a stable energy source over an exceptionally long period. Looking at the future, this system is likely to be a target for the James Webb Space Telescope or other powerful observatories, which might allow scientists to analyze the atmosphere of TOI 715b and any other planets in the system. If these atmospheres contain water vapor or even potential biosignatures, TOI 715 could become one of the best chances for studying a nearby star system that may resemble Earth-like conditions. But wait, there's more. Evidence suggests that there could be a second planetary companion of TOI 715b. If confirmed, this additional planet would likely have a radius about 1.066 times that of Earth, placing it in a similar size range, but slightly smaller than TOI 715b. This suspected second planet orbits at a distance that places it near the outer edge of the habitable zone. Its position suggests that, if it has the right atmospheric conditions, it too could potentially support water, or even lifelike processes, despite its location farther from the parent star. Imagine coming across not one but two planets that host intelligent life, and both of them orbit the same star. This could be the find of the millennium. The potential for these planets to support water, and by extension some form of life, is drawing interest from astronomers eager to use the powerful James Webb Space Telescope for detailed analysis. Given the proximity of TOI 715 at just 137 light-years from Earth, studying this system offers a unique opportunity to enhance our understanding of planetary systems around red dwarfs, which are the most common type of star in our galaxy. Detailed observations of TOI 715b and its potential companion can offer insights into the formation and behavior of small, close-in planets, particularly those around cooler stars. This knowledge could be crucial in understanding the diversity of planetary systems, especially those that may harbor life. So, how can the James Webb Space Telescope help us? The role of the James Webb Space Telescope. The James Webb Space Telescope, or JWST, was conceived as the successor to the Hubble Space Telescope, which revolutionized our understanding of the cosmos in the early days of the post-Cold War space age. Launched in 1990, Hubble was the first major optical telescope in space, orbiting above Earth's atmosphere to avoid distortion from atmospheric gases and pollution. From there, it revealed images of distant galaxies and star-forming regions, and provided insights into the expansion of the universe, capturing unprecedented detail that revolutionized our understanding of cosmology, the life cycle of stars, and the characteristics of planets within our solar system. Hubble's success was phenomenal. Its data revealed that the universe was expanding at an accelerated rate and helped refine the age of the universe to approximately 13.8 billion years. It also confirmed the existence of supermassive black holes at the centers of galaxies and helped us discover thousands of exoplanets. By the mid-1990s, the scientific community began envisioning a telescope that could observe the universe in infrared wavelengths, a range that Hubble's instruments were limited in capturing. Observing in the infrared spectrum allows astronomers to peer through cosmic dust and gas, which are opaque in visible light, but transparent in infrared. This capability is especially useful for studying the earliest stages of the universe, the formation of galaxies and planetary systems around other stars. In 1996, the concept of a next-generation space telescope received initial support from NASA, the European Space Agency, and the Canadian Space Agency. By 2002, it was officially named the James Webb Space Telescope. honoring NASA's second administrator, who played a key role in the Apollo program. The JWST required a massive engineering effort, as it needed to be significantly larger than Hubble to meet its mission goals. Unlike Hubble, JWST would be positioned about 1.5 million kilometers from Earth at the second Lagrange point, or L2, far beyond the reach of any repair missions. At L2, JWST would stay in a stable position relative to Earth and the Sun, making it easier to maintain consistent conditions for infrared observations. Moreover, infrared observations require extremely cold temperatures, so JWST was designed with a tennis court-sized sun shield to protect its instruments from solar radiation. JWST's primary mirror, which consists of 18 hexagonal segments, was made from lightweight beryllium and coated with gold. It could be folded up to fit within a rocket and deployed after launch. After several costly delays and testing, the JWST was launched on December 25, 2021. Once JWST reached L2 and completed its months-long deployment and calibration process, it began sending back stunning and transformative data. Since then, it has observed galaxies from only a few 100 million years after the Big Bang, allowing us to understand how the first stars and galaxies formed, how they influenced their surroundings, and how they contributed to cosmic evolution. Moreover, JWST's capability to observe in infrared wavelengths has allowed it to examine the atmospheres of exoplanets in extraordinary detail. Using a technique called transmission spectroscopy, JWST can identify molecular signatures, including water, carbon dioxide, and methane, revealing signs of life on distant worlds. JWST has taken detailed images of stellar nurseries, such as the famous Pillars of Creation in the Eagle Nebula, revealing intricate structures and processes involved in star formation. By observing the centers of distant galaxies, JWST has provided new insights into the role of supermassive black holes in galaxy formation and evolution. Overall, JWST's observations have dramatically expanded on Hubble's discoveries, providing a complementary perspective that builds on Hubble's optical and ultraviolet data with groundbreaking infrared insights. This has enabled astronomers to cross-reference data from both telescopes, leading to more accurate models of galaxy formation, the evolution of stars, and the chemical compositions of planetary systems. The JWST is expected to operate for at least a decade, continuing to push the boundaries of astronomical research. The telescope will also work in tandem with future missions, such as the Nancy Grace Roman Space Telescope, which will focus on dark energy and the expansion of the universe, and the upcoming European Extremely Large Telescope, which will complement JWST's findings from Earth. With JWST, we can finally see if there are others out there. Naturally, NASA has identified TOI 715b as a prime candidate for further observation with the JWST, whose advanced technology allows it to detect key atmospheric signatures. One of the primary goals of using JWST for this study would be to determine whether TOI 715b possesses an atmosphere, and if so, to analyze its composition. Spectroscopic analysis from JWST could reveal traces of water vapor or other molecules that hint at conditions favorable for life. The existence of an atmosphere would also suggest that the planet can retain heat, potentially moderating surface temperatures despite its relatively low equilibrium temperature. The telescope can also reveal vital biosignatures and confirm the presence of life. If this happens, it would be the first finding of its kind, forever changing the way we look at the cosmos and our place within it. It will also open up new doors in astrobiology. Could TOI 715b be an ocean world? An ocean planet is one with a predominant uninterrupted coverage of liquid water, unlike Earth, which has significant land masses interspersed between oceans. These planets are theorized to lack substantial continents or islands and would have their surfaces entirely submerged. Ocean planets are thought to form under conditions where a planet develops an outer crust with low density and a water-rich composition, often due to a water-heavy formation process. As they form farther from their parent star and are rich in icy materials, migration into the habitable zone melts the ice layers, potentially resulting in a vast global ocean. Since the TOI 715b is located within its host star's habitable zone and has an estimated equilibrium temperature of -39 degrees Celsius, its surface temperatures could be low enough to retain liquid water if it possesses an atmosphere capable of maintaining a moderate greenhouse effect. Such an atmosphere could keep its oceans from freezing completely. So how would we know if 2IY715b is indeed an ocean world? Well, we'd expect to find a substantial amount of atmospheric water vapors that maintain a balance of greenhouse gases, stabilizing the surface temperature. Also, there would be no large land masses or continents, but the planet might feature seamounts, trenches, and deep ocean basins. And of course, there would be a liquid ocean surface extending tens to hundreds of kilometers in depth, with an ice crust forming on the lower layers if the planet's core is cold or lacking tectonic activity to maintain a warmer ocean floor. This configuration creates a stable, potentially habitable environment where life, if it exists, would adapt to a completely submerged lifestyle, relying on the oceanic chemical cycles rather than terrestrial ecosystems. But how will we be able to see any of this? Well, direct observation of water on distant exoplanets is challenging, particularly when it comes to confirming the presence of liquid water. However, astronomers have developed methods to infer the likelihood of water or oceans on exoplanets through atmospheric analysis. For TOI 715b, scientists could use spectroscopic analysis via instruments on the James Webb Space Telescope and the Hubble Space Telescope. One option is transmission spectroscopy. In this approach, as TOI 715b passes in front of its star, a small portion of the starlight will filter through its atmosphere. By analyzing the spectra of this filtered light, scientists can identify chemical markers indicative of water vapor or other components of a water cycle. We can also use thermal emission spectroscopy, which observes the infrared radiation emitted from the planet's atmosphere. By examining the temperature and radiative properties, astronomers can infer the presence of greenhouse gases like water vapor and carbon dioxide. If TOI 715b exhibits thermal properties consistent with greenhouse warming, this could support the idea of surface water maintained in a liquid state. Reflected light spectroscopy is another option for planets in closer proximity to their host stars. In this case, the reflected starlight from the planet itself can sometimes be observed directly. Analyzing this reflected light helps to assess surface and atmospheric properties. Specific albedo signatures could indicate cloud-covered skies, potentially caused by high water vapor, or an ocean below. So let's say that TOI 715b is indeed an ocean world. What would it be like? Well, if there is life in the planet's ocean, it might bear resemblance to certain extremophiles found on Earth, which thrive in high-pressure, low-light environments, particularly in Earth's deep-sea ecosystems. If TOI 715b has hydrothermal vents along its seafloor, these areas could support life forms that derive energy from chemical reactions rather than sunlight. On Earth, extremophiles such as thermophilic bacteria and tube worms thrive around hydrothermal vents, using sulfur compounds and other chemicals as energy sources. Without the benefit of sunlight, life forms on TOI 715b might evolve to use chemosynthesis, converting chemicals from the ocean floor into energy. This could result in organisms resembling Earth's archaea, which flourish in deep-sea environments without light. Moreover, water pressures in TOI 715b would likely be immense at greater depths. Organisms will have to develop specialized cellular structures that can withstand high-pressure conditions. These can include flexible exoskeletons or pressure-resistant cell walls. The commonness of ocean worlds across the galaxy is becoming increasingly accepted among scientists. Ocean planets are thought to form readily in the protoplanetary disks surrounding young stars, accumulating large amounts of water ice that later melts when such planets migrate inward to warmer, habitable zones. Jupiter's moon Europa and Saturn's moon Enceladus are prime examples in our solar system of potential ocean worlds, covered by icy crusts with liquid water oceans underneath. Studies suggest that planets with significant water content might outnumber rocky, Earth-like planets in the galaxy as they form more easily in icy regions of protoplanetary disks before potentially migrating closer to their stars. But wait, there's more. The Small Planet Radius Gap and its implications. The Small Planet Radius Gap is a distinct pattern seen in the sizes of exoplanets where there is an apparent scarcity of planets with radii between about 1.5 and 2 times that of Earth. This intriguing gap, observed in exoplanet populations orbiting close to their stars, provides insights into how planets evolve and how various factors influence their compositions, atmospheres, and overall stability. Instruments like the Kepler Space Telescope revealed that planets orbiting relatively near their stars seem to cluster around 2 distinct size groups: super-Earths, which are slightly larger than Earth, and mini-Neptunes, which are around 2 to 3 times the size of Earth. Planets with radii between these 2 groups are conspicuously rare. This is what we call the small planet radius gap. Scientists think this happens because planets in this size range can lose a lot of their atmosphere over time. When a planet is close to its star, it gets a lot of energy in the form of heat and light. This energy can blow away a planet's atmosphere, especially if it's small and doesn't have enough gravity to hold on to it. So planets either end up small with no gas around them, or big with a thick gas atmosphere. TOI 715b, which is a little bit bigger than Earth, is important because it could help scientists understand why planets in this size range are so rare. Since it's in a sweet spot for having water, studying it could help scientists figure out how planets around red dwarf stars behave. For example, by understanding how it might have kept its atmosphere, even though it's close to its star, we can learn more about how planets in the radius gap evolve. It might also tell us if planets like this could support life. While this is all pretty exciting, we must not forget how all of this became possible in the first place. NASA's TESS mission and its discoveries. Launched in April 2018, NASA's Transiting Exoplanet Survey Satellite, or TESS mission, has become one of the most powerful tools in the search for Earth-like planets beyond our solar system. TESS's mission is clear: to find and study exoplanets, especially those that are similar in size and temperature to Earth. TESS is NASA's follow-up to the Kepler Space Telescope, which made groundbreaking discoveries about exoplanets but was limited by its field of view. Unlike Kepler, which observed a small patch of sky, TESS has a much wider view, covering about 85% of the sky. This expansive coverage allows TESS to identify planets orbiting nearby stars, with a focus on stars that are relatively close to Earth, at distances of up to 300 light-years. By studying stars near us, TESS can provide a more detailed understanding of planets that may have similar conditions to Earth. Since its launch, TESS has been conducting surveys using the transit method, which involves watching how a planet passes in front of its star, causing a slight dip in the star's brightness. By measuring this dimming, TESS can detect the presence of planets and, with follow-up observations, estimate their size and orbit. While TESS provides crucial data on exoplanet size and orbital characteristics, it is often not able to determine the mass or composition of a planet on its own. That's where ground-based telescopes come in. Once TESS detects a planet, scientists use telescopes on Earth to take additional measurements. Astronomers can then determine the planet's mass and density. These measurements help scientists figure out whether the planet is rocky, like Earth, or made mostly of gas, like Jupiter. For example, if a planet is about the same size as Earth but has a much lower mass, it might have a thick, gaseous atmosphere. If it's denser, it's more likely to be rocky, with a solid surface. By collaborating with ground-based telescopes, TESS can provide a much fuller picture of these distant worlds. As TESS enters its 6th year of operation, scientists are looking forward to many more exciting discoveries. The mission is designed to survey the sky in stages, and each stage allows TESS to focus on different parts of the sky, revealing even more planets. In the coming years, TESS is expected to discover many more planets that could support life, expanding our knowledge of what conditions are required for life to thrive elsewhere. Now, we come to the main question. Are we alone? Physicist Enrico Fermi once famously asked, "Where is everybody?" While the galaxy is teeming with billions of stars, many with planets in habitable zones, we have yet to find any concrete evidence of alien civilizations. Given the age of the universe and the vast number of potentially habitable planets, if intelligent life is common, we should have encountered it by now, or at least have detected some signs of its existence. Yet, the universe remains silent. This silence, which is called Fermi's paradox, is one of the biggest puzzles in modern science, and one of the key challenges in astrobiology. Over the years, several possible explanations have been proposed. Perhaps intelligent life is incredibly rare or short-lived, making it difficult for civilizations to overlap in time. Another possibility is that advanced civilizations are deliberately avoiding us, or that the signs of life are too faint or distant for us to detect. Whatever the case, we are closer than ever to answering the question of whether we are alone in the universe. With the advent of advanced telescopes like the James Webb Space Telescope and the Transiting Exoplanet Survey satellite, we now have the tools to observe exoplanets with unprecedented detail. While TOI 715b is an exciting discovery, it is by no means unique. There are other exoplanets in the habitable zone that could share similar characteristics. For example, TOI 700d, another test discovery, is an Earth-sized planet also located in the habitable zone of its star dot. The Kepler mission has also identified a range of exoplanets that could potentially support life. These planets are typically rocky and similar in size to Earth, making them prime candidates for further study. In the coming years, we can expect to find even more potentially habitable planets, thanks to the ongoing work of TESS, JDIST, and other space telescopes. As we refine our search for life, we will not only focus on planets that could have similar conditions to Earth, but also consider the possibility of life elsewhere in the universe. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.